This is Heliox, where evidence meets empathy. Independent, moderated, timely, deep, gentle, clinical, global, and community conversations about things that matter. Breathe easy, we go deep and lightly surface the big ideas. When you think about chaos, in the natural world, particularly in physics, what's the ultimate source of disorder? For physicists, it often boils down to one fundamental microscopic dance.
Brownian motion.
Brownian motion, exactly. Yeah. It's that perpetual, just utterly random, frenetic jitter of microscopic particles suspended in a fluid.
Yeah, they're constantly being smacked around by the fluid molecules themselves.
It is the purest, simplest form of disorder you can find in a liquid state.
It really is. It's the very definition of statistical randomness. And if you're an optics physicist, your gut reaction, your training, everything tells you that when you introduce something highly sensitive...
Like light.
Right, like light, and specifically the intrinsic angular momentum of light, its spin... When you put that into a system defined by this level of continuous spatiotemporal chaos,
it should be destroyed.
The result should be total destruction. Any coherence, any delicate order should be scrambled beyond recognition.
You'd expect a blurry mess.
You should end up with a blurry, depolarized, unpolarized mess where any measurable signal just, approaches zero.
That deep-seated expectation that disorder equals destruction is precisely what makes the sources we are diving into today so compelling.
I agree.
We are exploring the discovery of the Brownian Spin-Locking Effect, or BSLE.
Right.
And this breakthrough comes from a really powerful international collaboration. We're talking researchers like Xiaozhang, Peiyang Chen, Mei Li, Yuzi Shi, Erez Hasman,
Bo Wang, and Qianfeng Chen, a really impressive group.
Working across Shanghai Jiao Tong University, the Technion in Israel, and Tongji University in China, a global effort.
And the initial mission, which was largely driven by Bo Wang, who really spearheaded both the theory and the experimental design.
Okay.
It was a deceptively simple one. Take a chaotic soup of nanoparticles, blast it with light, and see if they could detect any faint trace of order.
And what they found wasn't faint at all.
Not at all. It was a robust, macro-scale phenomenon that fundamentally overturns that core assumption, that thermal disorder is always the enemy of these kinds of physical effects.
So the big puzzle for us, and the core of this deep dive, is that paradox itself. How can spatiotemporal chaos particles, constantly moving, colliding, fluctuating, how can that not only preserve light's fundamental property, its spin, but actually amplify it?
Amplify it into a huge ordered pattern.
A large macro-scale ordered pattern visible across distances measured in centimeters. I mean, we really need to understand the mechanism here. How does this chaotic system act as a perfect filter, locking the spin of the light in place?
And this is where the relevance hits home for you, the listener. You might initially file this away as, deep theoretical physics.
Very easy to do.
But the methods that are derived from this discovery offer a universal, scalable, and remarkably simple new tool for metrology.
The science of measurement.
The science of measurement, exactly. It allows scientists to measure the fundamental properties of tiny things like nanoparticles accurately, quickly, and robustly, even when they're suspended in the messiest, most chaotic environments you can imagine.
And that has immediate and profound applications across chemistry, pharmacology, biological research.
Advanced material science all over the world. It's a really big deal.
Okay, let's unpack this. We have to start with the foundation, Brownian motion. We know it's the chaotic movement of particles, but let's just, take a second to remember the historical and physical significance here.
For sure.
In this experiment, they're using gold nanoparticles, AUNPs, suspended in water.
And the key mechanism is the constant thermal fluctuation of the fluid itself. The water molecules are moving randomly just because of heat, and they are constantly bombarding these suspended gold particles from all sides.
It's like a microscopic game of pinball.
It is. And since the collisions are stochastic, they're imbalanced from one moment to the next. So the nanoparticle gets jolted in this erratic, completely unpredictable trajectory.
You can't know where any single particle will be in the future.
It's unknowable.
And this is physics that has stood the test of time, right? I mean, this isn't a new concept.
Absolutely not. It's actually, it's pretty humbling to think that the mathematical description of this has been a cornerstone of statistical physics since Albert Einstein.
1905.
His landmark paper in 1905. He provided the first definitive mathematical proof of the existence of atoms and molecules.
By explaining this motion?
By explaining the motion of pollen grains that the botanist Robert Brown had seen decades earlier. He established that the mean square displacement of these particles is proportional to time. We are still building on that cornerstone over a century later.
So the chaos itself is mathematically predictable in the aggregate, even if the individual particle's movement is totally random.
Yes, statistically it's very well defined.
And that very chaos, as you mentioned, is actually leveraged in technologies we already use.
That's correct. The diffusion properties of Brownian particles are they're the heart of a widely used optical technique called dynamic light scattering, or DLS.
Okay, DLS.
DLS is pretty much the industry standard for measuring the hydrodynamic diameter of nanoparticles.
And how does that work?
Well, if a particle is small, it diffuses through the water faster, right? Gets knocked around more easily.
Right.
This causes the intensity of the light scattered off of it to fluctuate very, very rapidly.
And a bigger particle.
A large particle moves more slowly, it's more sluggish, and so the fluctuations are slower. By tracking the decay time of these fluctuations, DLS can precisely calculate the particle size.
So the research team used this established method, DLS, not as their main tool, but more like a check on their system.
That's right. It was a sanity check. They used DLS on their gold nanoparticle samples just to confirm they were operating squarely within that chaotic regime they needed to be in.
And what did it tell them?
Their measurement confirmed that the scattered light intensity showed strong fluctuation above a characteristic timescale of about 0.7 milliseconds.
0.7 milliseconds.
Yes, and this is the coherence time. It's the time window during which the scattered fields maintain a stable phase relationship with each other.
And why is that specific timing, that 0.7 milliseconds, so crucial for the entire discovery?
It's absolutely critical because the camera they use to capture the macroscale spin effect had an acquisition time of about 2 seconds.
2 seconds, that's a lot longer.
A lot longer. Think of it this way. 2 seconds is roughly 2,800 times longer than the 0.7 millisecond coherence time.
Wow.
So every single snapshot they took was, in effect, a massive average over thousands of independent, entirely incoherent scattering events.
So there was no chance of any lingering coherence messing with the results?
None. This guaranteed that their observations were conducted firmly in the incoherent region. It means they were dealing with the full, unadulterated chaos of the Brownian system.
Which proved that the order they saw was being generated by the disorder, not just happening in spite of it.
Exactly. That's the key.
That sets the stage perfectly for where the BSLE fits into the broader field of optics in random media. Because up until this discovery, most of the groundbreaking work involved waves interacting with structures that were disordered, yes, but often static.
Or at least possessing a high degree of internal coherence.
Yeah.
Exactly.
Right.
The sources cite a really fascinating lineage of established phenomena that, inspired this work. You mentioned a few in the setup, like Anderson localization.
Can you just briefly remind us what that is?
Sure. In a nutshell, that's where light, instead of diffusing outward like you'd expect, gets permanently trapped or localized in a highly disordered but fixed medium.
So the randomness is frozen in place.
It's frozen. It's like a perpetual echo chamber for light created by the randomness.
And then you have other things like super oscillation.
Yes, that's where a wave packet can be made to oscillate faster than its fundamental Fourier components would typically allow. It lets you create super resolved images beyond the classical diffraction limit. It's a really neat trick of wave physics.
And the whole effects of light.
Also very cool. Those involve light separating based on its spin or its orbital angular momentum. So the light's handedness dictates its trajectory as it moves through a medium. These are all beautiful demonstrations of complex wave phenomena.
But the critical distinction, if I'm understanding this correctly, is that even when these systems are disordered, they are usually coherent and static.
That is the traditional paradigm,
Yeah.
and it's also the traditional problem. The position of the randomness is fixed in space, which allows the light waves time to interfere with each other.
And that interference is usually destructive.
It is. In these coherent systems, when you increase the level of fixed structural randomness, delicate physical effects like spin separation tend to just break down.
They get washed out.
The massive amount of randomness causes powerful destructive interference waves, canceling each other out perfectly. And this means the average measurable spin splitting effect just approaches zero. You end up with the expected messy blur.
So the goal then for Bo Wang and the team was to find a universal way to observe these spin effects in a truly disordered environment, but without that destructive interference.
Which meant they needed a system that wasn't just messy in space, but messy in time. They needed temporal chaos.
Okay, so before we jump into their setup and the big discovery, let's make sure we're all aligned on the core concept they were observing, the spin of light.
A good idea. When we talk about spin in light, we are discussing its intrinsic angular momentum.
This isn't the light ray spinning around its own axis like a tennis ball, is it? It's a common misconception.
But that's a good clarification. It's not a physical rotation like that. It's related to the rotation of the electric and magnetic field vectors as the light propagates through space.
And we measure that as polarization.
We measure it as circular polarization, right-handed versus left-handed. If the electric field vector rotates clockwise as the light moves toward you, that's one spin state. Counterclockwise is the opposite state.
And it's a fundamental property. It dictates how light interacts with materials.
Absolutely.
So how does that spin interact with the light's path? That brings us to spin-orbit interactions, or SOIs.
SOIs are the fundamental coupling where the light's spin its circular polarization dictates, or is dictated by its path or its momentum.
It's a feedback loop.
It's the idea that how light is twisting affects how it moves, and how it moves affects how it twists. A feedback loop between rotation and translation is a perfect way to put it.
Now, traditionally, to observe these SOIs, researchers had to be, well, engineering prodigies, right? It was hard.
Historically, yes. Observing these effects often required meticulous, painstaking engineering. You needed to introduce asymmetry deliberately into your system.
How would you do that?
You might set up a highly asymmetric illumination, like shining light obliquely at surfaces. Or you'd have to fabricate these intricate structured materials called meta-surfaces.
Tiny pattern structures.
Exactly. Tiny pattern structures that are designed to force the light to twist or follow curved paths based on its spin. A lot of work.
It sounds like traditional optics required researchers to meticulously engineer that asymmetry. So is the primary goal here to prove that nature, via chaos, could provide this asymmetry naturally without all that painstaking construction?
That was the foundational quest. That was what Bo Wang and the team set out to find. They were looking for a universal natural mechanism that reveals this spin separation independent of any of those engineered structures.
They wanted a system where light scattered off a simple isotropic object, a perfect sphere, in a natural flowing medium and still showed a robust spin effect.
They were aiming for universality.
Okay, let's get to the moment of discovery. The sources describe the BSLE as unforeseen, which suggests they set up an experiment expecting to see maybe a subtle, localized effect.
Right, maybe a tiny signal buried in noise.
And instead, a much larger, more robust phenomenon emerged. What was the core finding?
The core finding was that when they shone linearly polarized light into this spatiotemporally disordered Brownian medium, the constantly fluctuating gold nanoparticles in water, they observed not a blur, but a large-scale, robust spin-locking effect.
So we're back to the paradox.
We are. The disorder and thermal fluctuation, which should have completely scrambled the spin fields,
actually caused a clear, stable spatial separation of the light.
a separation into two regions of opposite spin components. They literally saw the light splitting based on its inherent rotation.
So one region had left-handed spin.
And the opposite region had right-handed spin angular momentum. It was as clear as day.
And the scale here is so critical. How large was this split?
It was macro scale. The observed spin separation reached a centimeter scale in the diffusion plane.
A centimeter.
For context, in the realm of disordered structures where these effects are usually measured in microns, maybe even nanometers, a centimeter scale splitting is enormous.
So this is off the charts, comparatively.
The sources specifically note this as the largest reported spin split achieved in disordered structures to date. And crucially, within these large regions, the spin fluctuation was measured to be remarkably small.
Meaning the effect wasn't messy?
It wasn't messy. It was homogeneous, stable, and locked.
It sounds like the system, despite all its internal chaos, was broadcasting a clean, clear macro signal. It's an ordered pattern emerging from underlying turmoil.
And the beauty of this discovery is that the setup itself was stunningly simple.
Right.
Which just reinforces the universality of the effect. They didn't need a billion-dollar clean room or high-end fabrication tools.
So walk us through it. What did it look like?
It was a standard optical setup. A linearly polarized laser, specifically a 639 nanometer wavelength with a beam width of about 2 millimeters, was aimed normally, so straight in.
Onto a simple glass container.
Just a glass container filled with the gold nanoparticles suspended in water.
So no curved mirrors, no metasurfaces, no fancy equipment, just light hitting a cup of agitated liquid.
Exactly. The real key was the observation geometry.
Okay.
The detection system was set perpendicular to the incident wave's momentum. So think of the light path moving along the x-axis. They observe the scattered light along the y-axis
At a 90-degree angle.
at that specific 90-degree angle.
Yeah.
And in that direction, the scattered light naturally divides itself into two diffusive regions, an upper region and a lower region, relative to the incident laser path.
Why is that perpendicular angle so important? Is it the geometry itself that causes the symmetry to break?
It is. It's a fundamental consequence of the physics. When linearly polarized light hits a spherical object, the resulting scattered field, when you view it perpendicular to the original direction of travel, intrinsically contains a spin component.
So it's a natural geometric consequence.
It's a natural geometric consequence of taking a 2D polarized wave and forcing it into a 3D scattered field. This is the seed of the entire spin effect.
Okay, so they have the scattered light at 90 degrees. It's split into an upper and a lower region. How do they actually measure the spin? How do they see the right-handed versus left-handed polarization in those regions?
They used standard optical components, a quarter wave plate, or a QWP, and a postpolarizer in the detection path.
Okay.
The quarter wave plate converts circular polarization into linear polarization, which the polarizer can then filter. So by rotating the QWP, they could selectively measure the intensity of the right-handed light, which they call IR.
And the left-hand IR.
Exactly.
Okay.
And they quantified the spin using a normalized parameter to find the difference in these intensities divided by the total intensity.
So 6 Sikar is IR/IL divided by IR plus IL.
Precisely.
And when they captured the image, what did the result look like?
It was striking. You could see the central unscattered laser beam, they call that the ballistic region, and then extending horizontally on either side of that beam path were two large, bright, diffusive regions.
And the spin.
The light in the upper region showed one spin angular momentum, say right-handed spin, whereas this is positive.
And the lower region.
The lower region showed the exact opposite left-handed spin, where Sickles is negative. This was definitive proof of the Brownian Spin-Locking Effect. It was a clear, large-scale, two-stream sorting of light based on its spin.
Achieved purely by shining light into a chaotic liquid. Incredible.
It really is.
An initial reaction from a skeptic might be, okay, this is just a unique interaction with the specific 250 nanometer gold particles you used.
A fair question.
So how did the researchers establish that this was a universal physical law and not just a fluke of their material choice?
This is where their control experiments become absolutely crucial, because they validate the universality of the mechanism. They perform several tests. First, they just changed the size of the gold nanoparticles.
They started with 250 nanometers?
They started with 250 nanometer diameter particles, and then they repeated the experiment with larger ones, around 400 nanometers in average diameter.
And what happened when they changed the particle size?
The entire spin pattern flipped its sign.
Flipped
Completely. So if the 250 nanometer particles resulted in right spin in the upper region and left spin in the lower, the 400 nanometer particles resulted in left spin and right spin down.
Wow. Okay, that's incredibly important.
It is. If the effect were purely due to the random movement, the sign wouldn't change. The fact that the sign flips depending on the particle size is definitive evidence that the macroscale effect is fundamentally dictated by the nanoscale physics of the individual scattering event.
So the geometry, that perpendicular observation, dictates where the split occurs, but the particle size dictates the direction of the split.
That's it.
It's a direct connection between the particle's internal electromagnetic resonance and the bulk macroscopic light diffusion.
Precisely. It confirms that the spin is generated at the particle level, and the Brownian motion is simply the transmission medium that allows that signal to be accumulated and preserved.
They also tested for material independence, didn't they? They didn't just use gold.
Yes, they did. They demonstrated the phenomenon using materials other than gold, like Fe3O4, that's iron oxide nanoparticles. The effect remained robust.
Which suggests the BSLE is not tied to the specific metallic properties of gold,
but rather to the universal optical properties of spherical scattering objects. It's a general phenomenon.
And what about concentration? I mean, this is a multiple scattering effect. What happens if you increase the density so much that light can hardly travel at all?
They pushed the limits. They demonstrated that the BSLE survives even at very high concentrations, where multiple scattering completely dominated the entire process.
How high are we talking?
At these extreme densities, the central ballistic, the unscattered laser beam, actually disappeared completely. It was 100% scattered.
So no light made it through cleanly?
Not a bit. And if this were just a simple single scattering event, the signal would likely degrade completely. But the fact that the macroscale spin split persisted and remained clear at this high concentration is critical proof that the process relies on the accumulation of spin through multiple incoherent scattering events, not just the first one.
So the universality is proven. It works with different materials, different particle sizes, which can even flip the sign, and under conditions where light is scattered hundreds of times.
Correct.
This really elevates the discovery from a lab curiosity to a ubiquitous, fundamental physical phenomenon of light interacting with thermal disorder.
It does.
Okay, we've seen the effect, and we've proven its robustness. Now we have to address the core paradox. How does chaos enable order?
The big question.
This is where Bowen's initial theory, which describes the two essential physical processes, comes into play.
And the theory is really beautiful because it's a perfect collaboration between order and disorder. The first step involves an ordered universal principle, and the second step involves leveraging the chaos to protect that principle.
Okay, let's break it down. Part 1.
Part 1. Intrinsic spin-orbit interaction from nanoparticles. The theory states that the act of scattering light off a single, isotropic spherical nanoparticle universally generates a radiative spin field. We talked about this. This symmetry breaking occurs naturally in that specific observation direction they chose, perpendicular to the incident momentum.
Okay, so we established that every single particle creates a localized spin signature. But how does that spin survive the trip across the container?
And that leads to part 2, incoherent multiple scattering, the role of chaos.
Right.
This is where the Brownian motion is not just a nuisance, but it's the hero of the story.
It's the key ingredient.
It is. The continuous erratic thermal movement of the particles causes these rapid temporal density variations. And this dynamical disorder achieves two things simultaneously. First, it ensures that the spin distribution generated by one particle is preserved.
And second,
And this is the most critical part, it eliminates the destructive interference that would absolutely plague a static coherent system.
that elimination of destructive interference is the key concept. Why is movement chaos better than stillness order at preserving this subtle spin field?
Think about it this way. In a static system, all, say, 600,000 particles are fixed in place. When light is scattered multiple times, the waves arriving at your detector all maintain a fixed phase relationship with each other.
Okay.
So if one scattered path has a crest and another has a trough, they cancel out.
And you get nothing.
You get zero net spin signal. If the system is perfectly coherent and symmetric, the total integrated spin approaches zero.
It's like trying to build a castle with Lego bricks, where every fifth brick is designed to explode the castle. It's stable, but it's fixed for failure.
That's a great analogy. Exactly. But in the Brownian system, the particles are moving so fast. Remember, the system coherence time is 0.7 milliseconds, but the observation is 2 seconds long.
Right.
By the time the next light field arrives at the detector, the scattering particles have all moved randomly. And this rapid movement ensures that the phase relationships between the scattered waves are entirely random over time.
So the destructive interference still happens, but it happens at random times and in random places.
Yes.
Meaning over the 2-second exposure, the average destructive effects just cancel each other out, while the fundamental underlying spin signature is allowed to accumulate.
That is the core insight. The movement enforces what's called temporal decoherence. You are left with the underlying signature of the spin effect, free from the destructive phase cancellation. The chaos is, paradoxically, the noise reduction mechanism.
Let's deepen this distinction between accumulating spin in a coherent system versus this incoherent system, maybe using the team's simulation framework.
Okay, so they simplified the theory into a two-step scattering model. Step 1, the incident light, $, hits a particle in the ballistic region, creating a source field, $, which is defined by the universal Mie scattering matrix.
And step 2.
Step 2, $, hits another particle in the diffusion region, creating the final scattered field, $. The complex part is calculating the total field you detect after thousands and thousands of such steps.
So if they were modeling a static, coherent system, they would just sum the fields, right, with all the phase information?
Yes. In that hypothetical coherent case, which they show in their figures, you would sum the electromagnetic fields, the E fields, from all particles, retaining the phase.
And what did that simulation show?
It showed intense, random, rapidly fluctuating bright and dark spot speckles, and the resulting average spin split was severely reduced or virtually eliminated.
Because summing the fields allows the destructive interference to just dominate everything.
It dominates. But the BSLE is incoherent. so they had to sum the result differently.
How did they do it?
In the incoherent case, which matches the BSLE, they project the scattered field A dollars onto the spin-up and spin-down states to get the intensities, 9 tau dollars. And crucially, they then sum the intensities, not the fields, over all the 600,000 plus nanoparticles in the simulated volume.
Because that's what a long camera exposure actually does. It averages intensities.
It's the only mathematically correct way to describe an averaging process that lasts far, far longer than the coherence time.
And the result of summing the intensities was the opposite of chaos.
Exactly. This accumulation of intensities, protected by the temporal chaos, led to the distinct, robust, and beautifully smooth macroscale spin fields that they observed in the lab.
The theory perfectly mirrored the experiment.
Perfectly. It confirmed that the temporal fluctuation from Brownian motion reestablishes the necessary symmetry-breaking condition by essentially eliminating the destructive interference that coherence would introduce.
And the smoothness of the observed spin field, which they characterize with beta distributions.
Yes, the narrowing beta distributions in their analysis further confirmed this stable large-scale order.
It's just a huge shift in perspective. We usually see randomness as something to be overcome or averaged out. Here, randomness is the mechanism that allows a subtle fundamental pattern to aggregate and reveal itself.
To truly appreciate the BSLE, we really need to understand the single particle scattering event.
Right, the very first step.
Why does a light wave hitting a perfect sphere inherently generate a spin field in the scattered light? This takes us into the deeper physics of Mie scattering and multipoles.
Okay, Mie scattering describes how light interacts with spheres that are roughly the same size as the wavelength of the light. Correct.
That's a good starting point. More generally, it is the rigorous theoretical framework for describing light scattering off spherical particles of any size. It involves solving Maxwell's equations for that specific geometry.
And the solution isn't just one simple formula.
No, it's a superposition of different electromagnetic modes, which we call a multipole expansion.
What are these multipoles?
They're essentially standing wave patterns of the electric and magnetic fields inside and outside the sphere. The simplest one is the electric dipole.
But you also have the magnetic dipole, electric quadrupole, and so on.
Exactly. And the intensity of each of these modes is determined by coefficients and Ball dollars, which are a complex function of the particle size and its internal refractive index relative to the surrounding medium.
And this framework is what proves the origin of the spin.
Yes. The spin-orbit interactions of the scattering originate from the non-diagonal components of the Mie scattering matrix, which they call dollar. This matrix mathematically describes how the incident polarization, say linear, is transformed into the scattered polarization, which now has a circular component.
It's the transformation itself.
It's the transformation, the conversion of a 2D incident field into a 3D scattered field that naturally requires the coupling between polarization states. And this coupling generates the spin field in the scattered direction. It is a universal mathematical reality of converting the geometry.
You stressed earlier that for the BSLE to work, the spin had to be radiative. It had to propagate across the bulk medium, not just be localized at the surface.
Right.
Let's explore that difference between near-field and far-field spin.
Okay, so if the particles were extremely tiny, much, much smaller than the wavelength, we'd be in what's called the Rayleigh limit. And in that case, only the electric dipole term, $1, would be significant.
And what happens then?
In this case, the resulting spin angular momentum density is purely transverse. It's perpendicular to the direction of energy flow, and it exists only in the near field.
So the evanescent field right next to the particle's surface.
Exactly.
And how quickly does that near field spin die out?
Oh, it decays extremely rapidly. It follows the 10933 rule. Imagine shouting into a closet. The sound waves die instantly within a foot of your mouth.
So it's trapped.
The 10830 decay means the spin is essentially trapped near the particle's surface, unable to reach the next particle to participate in the multiple scattering process. The sources note that this field satisfies a unique spin-momentum locking relation in that near-field space, but it can't get out.
Okay, so the 250 nanometer particles they used must have been large enough to escape this near-field confinement.
Exactly. As the nanoparticle size increases, you excite higher-order multipoles, the magnetic dipole, the electric quadrupole, and so on.
And when those modes are excited?
The scattered spin fields become radiative. They propagate far away, partially aligning with the pointing vector, which is the direction of energy flow. And crucially, the decay is much slower. It follows a 102 of 2 rule.
So if 102 hours is shouting in a closet, 102 is just like shouting across a large auditorium.
That's a perfect analogy.
Mm-hmm.
The 102 decay ensures that the spin generated by one nanoparticle is persistent enough to travel across the liquid, interact with the next scattering particle, and accumulate constructively through that incoherent multiple scattering sequence.
This is the physical mechanism that allows the macroscale BSLE to exist.
It is. The 250 nanometer size for the gold nanoparticles was therefore carefully chosen or found to be in the sweet spot where these high-order radiative modes dominated.
The sources mention that the interaction between different multipole modes is key. For the 250 nanometer particles, they had electric dipole, magnetic dipole, and electric quadrupole terms, all coupling together. Why does this coupling matter for the spin?
The coupling is essential because spin angular momentum is a consequence of the interplay between the electric and magnetic field components. When these different multipoles, electric versus magnetic, or different orders like dipole versus quadrupole, are simultaneously excited and they have a specific phase relationship, they generate a net flow of angular momentum that can actually propagate.
The technical terms are pretty dense here. They mention the Janus dipole, which is defined by coefficients A$ equals IB Bellot 1. For a non-physicist, what does that coefficient relationship actually mean in terms of how the light radiates?
That mathematical relationship, A$ equals IB Bellot 1, means that the electric and magnetic dipole moments are equal in magnitude, but perfectly 90 degrees out of phase in time.
Okay, so it's a specific, optimized configuration.
It's a theoretically optimized configuration. In this Janus dipole scenario, the system radiates energy in one direction and almost none in the opposite direction. But more importantly for us, this combination ensures that the spin angular momentum itself becomes a robust far-field effect with that 102 head OK.
It creates a particle that naturally sorts and pushes the spin out powerfully.
Exactly. In the far field, the SAM generated by the scattering is approximately parallel or anti-parallel to the light's momentum, depending only on the observation angle. Similarly, the Huygens dipole, where A$ equals B$1, also preserves this far-field decay property.
And the gold nanoparticles they used?
They are perfect Janus or Huygens particles, but the general rule holds. When there is a non-zero phase difference between any two different multipole components, which is typical for metallic particles, the resulting SAM will propagate to the far field as a radial component. This is the condition that enables the bulk BSLE.
So the simple act of shining light on a 250 nanometer gold sphere creates a miniature, complex electromagnetic machine that inherently generates a persistent propagating spin field.
That's a great way to put it.
And we can tie this entire phenomenon back to an even more fundamental concept. Geometric phase.
Yes, the spin split is fundamentally a geometric phase effect.
Geometric phase, or Panchratnam-Berry phase, is the idea that when a system is transported through a cycle in parameter space, say, rotating a polarization, it acquires a physical phase shift that depends only on the path it took, not the speed.
That's right. And traditionally, achieving a visible geometric phase effect required engineered systems, rotating structures, coiled fiber optics, or curved optical paths. Here, the researchers demonstrated that this geometric phase naturally arises from the scattered 3D electric field produced by the spherical nanoparticles themselves.
A completely natural geometric phase generated just by the geometry of the scattering event.
Correct. The researchers showed mathematically that the off-diagonal elements of that Mies scattering matrix, which govern the coupling between polarizations, are dependent on the angular coordinate, which they call validable.
And that dependence on the geometry of observation is the definition of the geometric phase.
It is. It dictates the spatial separation of the spin components.
That's incredibly elegant. It means the geometric phase spatial profile, the actual pattern of the spin split, is determined only by the incident wave and the observation direction, regardless of the particle material or size.
Exactly. The particle properties only dictate how much signal you get, the efficiency of the scattering. But the fundamental physics of where the spin goes is purely a result of the scattering geometry.
Okay, we've established the BSLE as a universal physical discovery where chaos facilitates order. Now let's talk about the practical payoff.
Right, the application.
The sources describe this as a novel platform for precision metrology, a new way to measure the physical properties of nanoparticles.
And this is the application that truly excites the chemistry and biology communities, because the BSLE is macroscale, robust, and homogeneous, and because it carries detailed information about the individual nanoparticles through multiple scattering.
They could turn it into a tool.
They were able to develop a powerful new tool, spin-resolved optical spectroscopy.
How did they adapt their simple experimental setup from a demonstration of physics to a practical measurement device?
Well, they moved from a single wavelength setup to a spectral analysis setup. They replaced the single wavelength laser with a broadband source. Specifically, a supercontinuum laser which emits light across a wide spectrum from 430 to 700 nanometers.
And they swapped the camera for a spectrometer.
Crucially, yes. They replaced the camera in the detection path with a spectrometer.
So now they are measuring the spin, not just the intensity, but as a function of the color or the wavelength. They're collecting a spectrum of spin.
Exactly. The spin spectrum, 6 of lambda. And this is immensely valuable because the Mie scattering properties, and thus the spin effect, are highly sensitive to the wavelength of light relative to the particle size. So by collecting the spin across a spectrum, they get a unique fingerprint of the particle.
But doesn't the chaotic nature of the diffusion make it hard to focus their analysis? I mean, it's still a messy liquid.
Not at all. That's the homogeneity advantage of the BSLE. Since the spin distribution is almost perfectly homogeneous within the upper and lower diffusion regions, it's locked, remember?
Right.
They could simply use a pinhole to select a clean target area within that diffusive light region and collect the spectrum without worrying about localized chaotic fluctuations or speckles.
Which simplifies things a lot.
It simplifies the requirement for complex, high-resolution optical imaging systems, making it a much more approachable and robust technique.
So to prove this new method, they had to compare it against the established gold standards. What were their benchmarks for accuracy?
They compared their spin-resolved spectroscopy results against 2 trusted techniques, scanning electron microscopy, or SELC-EM,
Which gives you a picture, basically.
which provides direct visual measurement of particle size, yes, and traditional dynamic light scattering, DLS, which provides the hydrodynamic diameter based on diffusion speed.
And the goal was to show that their spin spectrum yielded particle diameters that matched the physical reality revealed by some.
That was the goal.
So how do you correlate a messy experimental spin spectrum captured from a chaotic liquid with a perfect theoretical curve for a particle size?
They ran a rigorous theoretical calculation. They generated theoretical spin spectral curves for a whole range of varying particle diameters based on my theory. Then, they compared these theoretical curves against their experimental data using a root mean square error analysis.
An RMSE analysis.
Right, and this process just identifies the theoretical curve that provides the absolute best fit to the experimental data.
But if the experiments are inherently chaotic, due to Brownian motion and concentration variations, how did they stop that real-world messiness from corrupting their comparison to the perfect theoretical curves?
That's a really key refinement in their methodology. They introduce a specific empirical factor into their RMSE calculation, a depolarization parameter.
How does that do?
This parameter, which sits between 0 and 1, just accounts for experimental variances, like the specific concentration of nanoparticles in the solution, which inevitably causes some depolarization due to the high scattering density.
So they're optimizing 2 things at once. The theoretical diameter, dollars, and this depolarization parameter.
Precisely. By optimizing both parameters simultaneously, they could find the perfect, most accurate match between the theoretical spin signature and the real-world, slightly depolarized experimental observation.
Let's look at the results then. How accurate was this new technique compared to the physical SEM measurement?
The correlation was exceptional. It really confirmed its viability as a metrology tool. For sample 1, which had a benchmark SEM measurement of 101 nanometers, the spin-resolved spectroscopy found the best theoretical match at exactly 100 nanometers.
Wow.
That translates to an astounding 99% accuracy.
That is highly competitive performance for any new optical technique.
It is. For sample 2, which was a nominally 150 nanometer particle, the best theoretical match was 135 nanometers, which yielded an accuracy of 89%.
Still very good.
And for sample 3, a nominally 200 nanometer particle, the match was 195 nanometers, resulting in 97% accuracy.
So this is not just a theoretical curiosity. It's an immediate practical application. It offers a highly effective and accurate alternative to more complicated methods.
Absolutely. Unlike SEM, it's non-destructive and doesn't require vacuum chambers. And unlike DLS, its measurement is tied to the intrinsic size-dependent optical resonance of the particle.
Not just its hydrodynamic diffusion speed, which I imagine is highly sensitive to things like temperature and viscosity.
Exactly. It validates the BSLE as both an important physical discovery and an immediate practical tool that could significantly accelerate analysis in many fields that depend on the quick, precise, and simple measurement of nanoparticle properties.
What a remarkable journey. We started with the ultimate source of disorder Brownian motion, a phenomenon that defined chaos in the mind of Einstein over a century ago. And we have ended with a macroscale, stable, and quantifiable signal, thanks to the insight of this team, including Xiao Zhang, Peiyang Chen, Mei Li, Yu Zixi, Eris Hausman, Bo Wang, and Xianfeng Chen.
The core takeaway is a really powerful counter-narrative in physics. The temporal chaos of the Brownian system was not something to be overcome. It was the essential enabling component.
It was a solution, not the problem.
It acted as a perfect natural decorrelation filter, stripping away the destructive interference that coherence would have imposed, and thereby preserving and amplifying the subtle intrinsic spin generated by individual nanoparticles through Mie scattering and geometric phase effects.
The significance, as the source material strongly implies, is the universality of the Brownian spin-locking effect. It is ubiquitous.
It is.
Because it works regardless of specific material or container shape, only the properties of the light source and the scattering geometry matter for the spatial pattern, this Brownian suspension essentially becomes a universal bulk spin-probing medium.
And this kind of fundamental breakthrough always inspires new research frontiers. The discovery suggests that similar effects might be waiting to be found in other wave-based systems.
It's like sound.
Perhaps acoustic waves or even quantum systems, where dynamical disorder might be leveraged to reveal ordered properties in a similar way.
The researchers themselves have pointed toward fascinating next steps. For instance, investigating the system dynamically by using much faster optical detection methods.
Right, moving beyond that 2-second average.
Or even slowing down Brownian motion dramatically by lowering the temperature or increasing the fluid viscosity to study the moment-by-moment generation and accumulation of the spin fields.
But the truly provocative implication is the engineering path.
Okay.
If the spin is entirely dependent on the specific multipole resonance of the individual particle, then scientists can use custom-designed nanoparticles or metamolecules in the suspension.
And if you allow these specialized particles to fluctuate thermally,
you could create a liquid metamaterial.
Wow. Imagine designing exotic light-matter interactions using a flowing dynamic liquid rather than being confined to fixed, solid, fabricated structures.
You could tune the optical properties of the bulk medium instantly, just by changing the concentration or the temperature. That truly turns the world of conventional fixed optics into a dynamic liquid science.
It's a whole new paradigm.
And this brings us to the final thought we want to leave you with. This entire discovery fundamentally shifts our view of randomness. Chaos isn't just noise destined to be eliminated. Under the right conditions, thermal disorder can be the most effective tool we have. A perfect natural filter stripping away complexity and revealing subtle fundamental patterns of order that were previously entirely obscured by our conventional orderly observation methods.
So the question becomes, what other complex, messy systems around us might be hiding universal physical laws, just waiting for the right type of incoherent approach to bring them into perfect macroscale focus?
Thanks for listening today. 4 recurring narratives underlie every episode: boundary dissolution, adaptive complexity, embodied knowledge, and quantum-like uncertainty. These aren't just philosophical musings, but frameworks for understanding our modern world. We hope you continue exploring our other podcasts, responding to the content, and checking out our related articles at helioxpodcast.substack.com.